Just give me a second, okay? Okay. So what's going to happen is that attendance link that I had sent, that attendance link will work only if we have a student ID, because one of the this one entries, one of the things that I have changed was you have to enter your student ID and then you can get attendance. Okay. But you see, for Google Meet, I have already given you the link for the Google Meet. We are going to use the same Google Meet link. So whether you have a student ID or not, please feel free to join my class and attend my class and listen to my lectures. Okay, I'm not going to stop any student from missing my classes. Okay, I really don't believe in that. I don't believe that knowledge should be bound. Okay, there's a poem by Rabindranath Tagore, where the mind is without fear. So that's a very inspiring poem. If you have read that poem, you know what I'm talking about. If you have not read that poem, please, I suggest that you go online and then find that poem. It's called "Where the Mind Is Without Fear" by Rabindranath Tagore. Here, in that poem, he describes how an ideal society should look like. So knowledge should be free. Okay, that's my belief. Okay, that's my very strong belief. Knowledge should be free, and whether you have a student ID or not, for whatever be the reason, for some of you the reason could be that the partial payment of fees. For some of you it could be that maybe you are thinking of going elsewhere. For some of you it's that maybe you have not received your results from your previous college. So whatever be the reason, you have different reasons for not having the student ID. But I'm not going to prevent that from I'm going not going to let that prevent you from attending my classes. Okay, you can attend my classes. Only thing will be, until you get the student ID, you will not be able to get attendance. That's all. That's the only thing that is going to happen. Okay, but you can still attend my classes and you can still get knowledge. Okay, whatever the subject you're supposed to learn, you'll still get that knowledge. Is that clear with everyone?
Yes, sir.
Okay.
Yes, sir.
I did not. Yeah, yeah,
Yes, sir.
okay. I did not want to, spell this out in the WhatsApp group or publicly. The reason is because this, as per the instructions that we have been given, we are supposed to take class for students who are registered at our university. That's the thing. But then uh, I would like to differ along with that. Okay, so that's the reason where I'm actually taking a step which is slightly different from what I have been instructed to do. Technically speaking, the only thing that's going to matter is that's the only thing that is going to reflect that you haven't got your student ID is the attendance, because your attendance will not be there, but you will still be able to attend the class. Okay, that's my promise to you. Okay, you will not miss my class. If you want to learn, you're all most welcome to attend my class. Fine. So that's how we are going to proceed. Okay. So I'm going to start today with the topic itself. So I wanted to first show you yesterday's class. I wanted to show you the syllabus. So let's first begin by showing you the syllabus. By the way, those students, those of your classmates who have not joined today, because it's possible that they might be thinking that they don't have their student ID, so they may not be able to join my class right now. If there are any of those students, please inform them individually. Don't send a message in the WhatsApp group, okay? All right. I hope you understand. No, in that
Yes,
WhatsApp
sir.
group, please don't send a message to them.
Yes.
You know who all your friends are. Just individually, one by one of you can just take a responsibility. Individually, you can just text them and please ask them to join now. All right. Okay. So I hope you can see my screen. No, is my screen visible?
Yes, sir.
No,
Okay.
sir.
So the course not visible.
No, sir.
You're not able to see. Who's not able to see?
It's me.
LG.
Yes.
Others, is it others are not also able to see? Let me just stop presenting and start again. Okay. Just let me know, okay, when my screen is visible.
It's visual, sir.
It's visible. LG, can you
Yes.
see that?
No, sir. I can't see. I'll.
Okay, I think there's some problem on your side, okay, because others are able to see. This lecture is recorded anyway, so you can watch the recording later on, okay, if you want.
Okay,
Okay,
sir.
for a time you just listen, okay, just be with us and listen. All right, so the course that I'll be taking is mathematical physics. Okay, the course that I'm taking is mathematical physics. Really, really important. Without maths you cannot understand physics. You cannot actually do physics. You can understand physics, but you cannot really do much of physics without mathematics. The objective of the course is basically that only, to lay the foundation, the mathematical foundation, okay, for understanding physics. Okay, there are 5 modules in this. The first and the second module, the first and the second module, even though the second module looks very few topics are there, but it takes a lot of time. So the first 3 modules, they're the biggest ones. First module is complex theory, okay, theory of complex functions. Then we have second module is vectors, and third one is special functions. So these are the 3 major topics from this course. And then we have integral transform, which is more application based. Okay, integral transforms, application based. And finally we have probability and statistics, just some basics of probability and statistics, which are most of you are familiar. And we will do maybe 3 distributions, yes, binomial, Poisson and Gaussian distribution, and some general property of probability distributions. That's it. We are not going to do much of this in detail. Okay, over here we're not going to do much in detail. You will do much more, a full module on probability and statistics next year. In your final year, in your third semester, there is going to be a paper called as research methodology. In that paper you will be learning probability and statistics in much more detail, as a single module, okay, as an entire module, as a consisting of many more hours. Okay, so what I'm going to do is, the plan here is, I will be spending I'll be first starting with module 1. Okay, because you all have learned complex theory. You all are already familiar with complex numbers. In your BSc you would have probably done complex numbers, so you are already familiar with complex numbers. So I'll be starting with the theory of complex functions. Then I'll move on to vectors and matrices. Then using the knowledge that we gain from these 2 modules, we'll build upon that, and we'll go to modules 3 and 4. Maybe after module 2, we'll take a little bit of break and we'll go to module 5, that is probability and statistics, because this is fun actually. Okay, so after module 1 and 2, I'll do module 5, then I'll go to module 3 and module 4. So this is basically the plan that I have for you. Okay, is that clear?
Yes, sir.
Any questions, any clarifications? If you have, please feel free to ask me now, or you can text me separately also, not an issue. I'm available. All right. Okay, so now we will start with the first one, that is complex functions. Okay, from the first module on complex functions. So for initially we will just be doing a little bit of fundamentals. Okay, so some just a kind of like a revision of complex numbers that you're already familiar with. Okay, so first we'll be doing that. Then we will introduce the idea of complex function. What exactly? Sorry, first a complex variable. Then we'll go to what complex functions are, and that's how we're going to proceed. Okay, so we'll define a kind of function which is known as analytic function. Okay, and how these analytic functions are actually very useful, and eventually we are going to apply this for in real applications. Okay, so here we go. So this is the outline for this lesson. We'll first do the fundamentals of complex numbers. That's basically a review of what about complex numbers that you're already familiar with. Then functions of complex variables. Just give me a second once. Okay, then functions of complex variables. Okay, and finally we'll do analytic functions. So these are the 3 things that we'll be doing in this lesson. There are totally 3 lessons that I have divided this module into 3 lessons. This is the first lesson. Okay. All right, so first, the different representations of a complex number. You all are already familiar with this. We represent complex number using the symbol Z, right? And there are many different ways by which you can represent them. The first way is by an ordered pair. You could have a number x and a number y. You could represent this x and y as an ordered pair inside a bracket. You could represent this, and we said that this is an ordered pair representation. So here x and y, what is this x and y? Any complex number will have a purely real and purely imaginary part. So this z that we have, okay, this complex number z that we have, okay, so this complex number, this is the complex number. We represent this using Z. It has a real part and it has got an imaginary part. Imaginary part. The real part is what we represent as x, and the imaginary part is what we represent as y. So here x and y, we first the first coordinate is like, coordinate system. We represent using coordinates. So first coordinate is the real part, and the second coordinate is the imaginary part. Then there's another way by which you can represent that. The real part is standalone. We leave it as it is. The imaginary part I multiply with I, and what is I? You already know what is I. What is this I? What is this I? It is actually referred to as iota. Okay. That's a Greek letter. It's an iota. What is this I? Can anyone tell me? You can unmute yourself. Let's have a discussion here. What is this I?
Root minus 1.
Yes, it is under root of minus 1. Okay, it is under root of minus 1. So that is your I. So when I say I, this is what I mean. This is under root of minus 1. Okay, because negative numbers you cannot find the root. Okay, negative numbers you cannot find the root. So that root is called as a purely imaginary part. Then this is known as, this representation is known as a algebraic form. Okay, so this is an ordered pair representation. This is an algebraic form. All of these forms that we have that I have written here, all of them are equivalent. Okay, so they're same. It's up to you whether you want to represent them as ordered pair or as an in algebraic form. That is real part plus I into the imaginary part. Then there is another form by which I can represent them. That is known as a polar form. Polar form is equal to r into cos theta plus I sine theta. And if you compare the algebraic form and the polar form, so immediately you get to know, for algebraic form and polar form, immediately you come to the realization that this real part is equal to r times cos theta, right? The real part is equal to r times cos theta, and the imaginary part y is equal to, because I, right, whatever is multiplied with I, and that is r into sine theta. Okay, so what is this r? R is basically the magnitude of this complex number, and theta is the angle that it makes, the complex number it makes with the real axis. Okay, so this is the polar form representation of complex numbers. And finally, the most user friendly, if I were to use that word, that form is known as the exponential form. Okay, the exponential form, we write it as r into e to the power I theta. We write it like this. And then when you compare the polar form, okay, when you compare the polar form with the exponential form, you realize, moment you compare these two, r is multiplied with something, here also r is multiplied with something, then this something and this something must be the same. That means e to the power I theta is equal to cos theta plus I sine theta. Okay, e to the power I theta is equal to cos to the power I sine theta. What is this formula called? What is this formula called? Anybody? You remember? E to the power I theta is equal to cos theta plus I sine theta. What is this formula called? Starts with E. Do you remember? Formula or notation? The Euler's notation or the Euler's formula. Okay, is that clear? Everyone?
Yes, sir.
All right.
Yes, sir.
Yes.
Next idea that we need to remember, we need to recall is the idea of a complex conjugate. Okay, what's a complex conjugate? Okay, by the way, this one, before I continue, is there anybody who did not learn complex analysis in your BSc? Is there anybody amongst you who did not learn complex analysis? Okay, so everybody has done that. So you all are familiar with this. That's great. Okay, so next topic is that of, the next idea is that of complex conjugate. So what is complex conjugate? Suppose I have a complex number z. Okay, so z is equal to x plus iy, which of course belongs to the set of all complex numbers. This is how we write down. then there exists its conjugate z star. So conjugate of z is written as z star, and this z star also belongs to the set of complex numbers such that when you multiply the conjugate with z, okay, so when you multiply the conjugate, the z star, when you multiply with the original complex number itself, that will give us the sum of the squares of the real part and the imaginary part. Real part is x, imaginary part is y, so the sum of the squares of the real part and the imaginary part. And then you can actually work backwards and you can find out that the complex conjugate is actually x minus iy. So all you need to do is whatever is the sign, okay, whatever is the sign before the imaginary part, that you just have to negate that sign, that's all. Okay, if it is plus, you have to make it minus. If it is minus, you have to make it plus. Whatever is the sign for the imaginary part, that is the part which contains I, whatever is the sign, you just have to negate that sign. Okay, so that is going to give us the complex conjugate. Next idea is that of a polar representation. So this kind of a diagram is known as an Argon diagram. Okay, so it's known as an Argon diagram. An Argon diagram, basically along the horizontal axis we have a set of real numbers, and the vertical axis we have set of imaginary numbers. Then this we represent a complex number in the form of a vector. Okay, we represent this in the form of a vector. So this arrow, okay, that is a complex number, which is z. Then the intercept that this vector makes with the horizontal axis, that intercept is x, and the intercept that it makes with the vertical axis, that intercept is y. So this is the real part and the imaginary part. So that's why this is known as the real axis, this is known as the imaginary axis. And this also gives you an understanding of what is this r and theta. R is basically the distance from the origin till the point, till this point, which represents a complex number. And theta is the angle that this vector makes with respect to the real axis. So this is basically your polar representation of Argon diagram. So extremely useful, okay, extremely useful in understanding complex numbers. Okay, and in fact for our analysis of when we're talking about analytic functions, we'll be actually resorting to Argon diagrams to understand the complex range and complex domains. Okay, so those are the things. So very useful. Okay, Argon diagram. So if some of these things you're not able to actually follow what I'm talking about here, so I strongly suggest that you go back to your BSc, pick up whatever book on complex numbers you had used in your BSc, and go through these fundamentals. Okay, because unless and until the fundamentals are clear, then you will not be, the rest of the chapter is not going to make much of a sense. Okay, so please do that. Then moving on, let me just clear the screen. Okay, so moving on, operations on complex numbers. You could add or you could subtract complex numbers. Okay, addition or subtraction of complex numbers is allowed. So I am having two complex numbers, Z1 and Z2. I could add them or subtract them, plus or minus. So adding complex numbers, okay, adding complex numbers is simply you add the real parts and the imaginary parts separately. Similarly, subtracting two complex numbers is in the same order. You subtract the real part and subtract the imaginary part. That is going to give us that new complex number. Okay, so real part, the addition or subtraction is the real part of the new complex number. Imaginary part of addition or subtraction of the imaginary parts will give us the imaginary part of the new complex number. So that is addition or subtraction. Next, you can multiply complex numbers. Multiplication of complex numbers, it's better to use the exponential representation. Okay, many different representations are there. For addition, the algebraic representation is easier. It's better to use the algebraic representation. You can again relate this here. Many different representations are there: ordered pair, algebraic, polar form, exponential form, and these different forms. For addition and subtraction, which form did we use? We used the algebraic form. Okay, the algebraic form for addition and subtraction. For multiplication, which form did we use? We used the exponential form. Okay, it's much easier to use exponential form because when you multiply them, it is just Z1 is equal to R1 e to the power I theta 1, and Z2 is equal to R2 e to the power I theta 2. So you're just multiplying the magnitudes R1 and R2, and the angles, they just get added up together. Okay. So likewise, you could divide also, division also. It's much better if we use, when you want to divide complex numbers, it's much better that we use the exponential form. The exponential form for division again. Okay, for division, we again use the exponential form. Much easier. You can use the other forms also, but division exponential form is what is used. So anything that helps to makes our job easier. Okay. All right. Okay, so again, this iota I, okay, this is the known as the imaginary unit. Okay, this is known as the imaginary unit. I is known as the imaginary I, which is equal to my root over -1. This is known as the imaginary unit, and this iota is represented as 0, 1. If you want to represent this in the form as an ordered pair, if you want to represent, this is represented as 0, 1, which you can easily see. How did we get this 0, 1? Because if we have the this is the argon diagram, this is the real part and this is the imaginary part. The imaginary part is a multiple of I, no? So if I take one unit here, that one unit is basically your I, and you can see here, if you consider this as the x-axis and this is the y-axis, the coordinates are 0, 1. So for that reason, the iota, that is root over -1, which is I, can also be written as 0, 1. Okay. Then I and its multiples are known as pure imaginary numbers. Okay, I and its multiples are known as pure imaginary numbers. There is I, twice I, thrice I, 7.6 I, 51.9 I, and so on. These multiples are known as pure imaginary numbers. Powers of I, another interesting property of the powers of I to the power 4n is always going to be equal to 1. Okay, where n is integers. Okay, n is integers. So if I you raised to the power of the fourth, the multiple of some integer, let's say n is equal to 3, so 4 times 3 is 12. I to the power 12 is equal to 1. Similarly, I to the power 4 n plus 1 is I to the power 4 n plus 2 is -1, I to the power 4 n plus 3 is equal to -I. You can actually think of it this way. Okay, it's much easier to remember it this way. So let's say, again, I consider the argon diagram. Let's again consider the argon diagram. So here, real axis, here we have the imaginary axis, the real and the imaginary. Let me use a different color where it becomes clear. Okay, so which is 1? 1 means this is purely real, right? So 1 unit, let's say this is 1 unit, this is 1, right? This number is 1. Then which is I is again 1 unit on the imaginary axis. This is I, which is -1. -1 is on the negative side of the real axis, so this is -1. And minus I is on the negative side of the imaginary axis, so this is -I. Okay. So now I to the power 4n, you can see here this image number that we have. This is I to the power 4n. Now what I do is, to this if I multiply, I again, I to the power 4n. If I multiply again, if I multiply I, then this is going to give us I to the power 4n plus 1, right? And 4 I to the power 4n plus 1, what is it equal to? It is equal to I, right? It is equal to I. So what happens is, when you multiply this number, when you multiply this with I, it rotates it counterclockwise by 90 degrees. Multiplication by I is equivalent to counterclockwise rotation by an angle of pi by 2. Does that make sense? Does that make sense? It's looking like a rotation, no? It's horizontal, then it becomes vertical. That means the way in which it should rotate is, it should rotate in the anti-clockwise direction by pi by 2. Okay, and how did we achieve that? By just by multiplying whatever is the number here, I to the power 4n, you multiply it with I. Multiplying this number with I will give us this number, which is I to the power 4n plus 1. Again, I to the power 4n plus 1, I to the power 4n plus 1 is there. Again, you multiply this with I. This is going to give us I to the power 4n plus 2. I to the power 4n plus 2, what is it? This is equal to minus 1. Minus 1 is over here. This is minus 1. This is minus 1. So what have you basically done? You have multiplied again, you have multiplied another I, you have multiplied by I. Multiplying by I again, it will rotate this by counterclockwise by 90 degrees. Again, when I multiply this with this I to the power 4n plus 2, and again I multiply this with I, again it's going to give us, next time it is going to give us I to the power 4n plus 3, which is equal to minus I, which is again, it looks like a counterclockwise rotation. Again a counterclockwise rotation, and we get minus I. Now what will happen if I multiply this again? Here, what is the number? The number here is I to the power 4n plus 3, which is equal to minus I, right? Minus I is basically this. What will happen if I again multiply this with, what will happen if I again multiply this with I? What will happen? It will become I to the power 4n plus 4, which is equal to I to the power 4 into n plus 1, which I can write it as I to the power 4m, where m is equal to n plus 1, right? And according to this one, n can be any imaginary number. It's just a dummy index, so it doesn't matter. So this will be, anyway, it's going to be equal to 1. So that means again you're going back to the real axis. Is that clear to everyone? Is that
Yes,
clear?
sir.
Yes, sir.
Yes, sir.
Okay, so this idea actually you can put to use. Okay, this idea you can actually put to use. So suppose I have a complex number. So remember this. Okay, multiplying by I. What does multiplication by I do? When you multiply any complex number with I, it rotates that complex number counterclockwise by how much? By pi by 2. Fine. So let us consider a number. Okay, z equals to 2 plus 3i. Z equals 2 plus 3i. That means 2 units along the real axis and 3 units along the vertical axis. So 3 units. So 2 here and 3 here. So somewhere over here. Okay, so this is the Z that we're talking about. So this is Z. So now if I multiply this with Iz, this is going to be equal to I into 2 plus 3i, which is equal to, multiply these, I square is equal to minus 1, no? I square is equal to minus 1, and this is going to be 2i, so minus 3, right? I square plus 2i. Minus 3 plus 2i. Minus 3 means along the real axis, this is the imaginary axis. Along the real axis, we have to go 3 minus 3. 3 units in the negative direction. So minus 1, minus 2, minus 3. And along the imaginary axis, 2 units, 1, 2, right? So this is what we get. So this is going to be the imaginary number. So this is going to be the complex number. So this number is your Iz. Now can you guess what will be the angle between them? This angle is going to be equal to pi by 2, because multiplying by I is going to rotate a complex number by pi by 2 radians. Is this clear?
Yes, sir.
Yes, sir.
Okay, so
Yes,
this
sir.
is not just for I, it holds good for any complex number. Okay, now if I again multiply with I, so what will I get? If I again multiply with I into Iz will give us minus Z, and which is minus Z? Minus Z is in the other direction. This angle will be again 90 degrees, right? This is minus Z. Again when I multiply this with I, what will I get? Minus Iz, right? So this is going to give us minus Iz. So this is also 90 degrees. Again when I multiply this with I, minus Iz into I will give us minus I square. I square will give us another minus and minus will give us plus 1. So again we go back to Z. So this rotation, by 90 degrees is a characteristic feature of this complex numbers. Okay, multiply any complex number with I, you'll rotate it by pi by 2 radians. Can I erase this?
Sir.
Yeah, let me just erase this. So anyway, the recording is there, going to be there with you. Okay. So I as a rotation operator, right? So you could actually formally prove this with the second part which I showed. No, Z, when you multiply I, it rotates it by pi by 2. You can actually formally prove this. So Z1, let's say Z1 is equal to Z, which is equal to R cos theta plus I sin theta, which can be written as R e to the power I theta, and I can be written as 0 plus I, 0 plus I, right? I can be written as 0 plus I because you just put a 0 in front, no real part, only imaginary part. Now 0 plus I, 0, cos of pi by 2 is 0, sine of pi by 2 is 1, right? So pi by 2 is the angle by which it rotates, so e to the power I pi by 2, okay? So if I multiply Z1 and Z2, I use the multiplication Z1, Z2 when you multiply R1, R2, e to the power I theta 1, theta 2, theta 1 plus theta 2. Theta 1 is equal to theta and theta 2 is equal to pi by 2. So Z1 is I, so Z1 is Z and Z2 is I. So I Z is equal to R e to the power I theta plus pi by 2. So this is the proof that this I rotates, it causes an anti-clockwise rotation by, it causes an anti-clockwise rotation by pi by 2 radians without any change in the magnitude. Okay, there is no change in the magnitude. The complex number, its magnitude remains the same. The length of the arrow remains the same. Okay, so this is the formal proof of what I had shown you some time back. Then we have some more relations. Okay, I'll just quickly go through. Cos of an angle can be written in terms of the exponential notation. You can actually very easily, you can prove this. Then similarly, we can, a sine also can be written like this. Likewise, we have representations of the hyperbolic cos and the hyperbolic sine in this way. Okay, so you can easily prove this using these representations. You can easily prove that the hyperbolic cos of Iz is equal to cos Z, and hyperbolic sine of Iz is equal to I sin Z. Okay, so I'll not go into the proof because this was probably done in your BSc. Then there is known as the De Moivre theorem. Okay, so it is cos theta plus I sin theta to the power n is equal to cos n theta plus I sin n theta. So again, this proof is not something that I'm going to do. It's an extremely useful theorem. You need to remember this theorem, and the proof, if you are interested, you can just go and have a look at your BSc textbook. Okay, so next is the inverse function. The inverse function. So just as you are able to find sine, just as you are able to find sine of this complex numbers, in the similar way you can find out inverse sine of complex numbers, and these are some of the formulas: inverse sine, inverse tan, inverse hyperbolic sine, inverse hyperbolic tan. Some formulas, just for your reference, I have given this over here. That's the only thing. Then relationship between circular and hyperbolic functions. Circular means the trigonometric functions, and the hyperbolic function. These are some relations between them. Okay, you can again proofs if you want of this. You have, I suggest you go through your BSc textbook. Then logarithmic functions, this logarithms, powers and roots, interesting properties are there. So if you try to take the logarithm of a complex number, that is like ln of z, that is, we are talking about natural logarithm. Okay, so ln of z, and I hope you know this ln of z. When I say ln of x, what does it mean? It means log to the log, not to the base 10. We are not taking log to the base 10, rather we are taking log to the base e of x. This is what I mean. This is the natural base. So natural base, the n come from there, L from logarithm, n from the natural base. So ln ln of x. So this is what I mean, ln of z, log e, log to the base e of z. Okay, so ln of z can be written in terms of the exponential notation as r e to the power I theta. So this can be written as ln of r plus ln of e to the power I theta. Ln and exponential, they are inverse relations of each other. You all are already familiar with this. Ln of e to the power x is x, right? Likewise, in a similar way, e to the power ln of x is also equal to x. Okay, so ln and exponent, they kind of cancel each other out. So whatever is operand that you are operating these two on, this operand remains the same. So you're taking ln of r plus ln of e to the power I theta. So ln and e, they will cancel out. So as a result, whatever is the exponent, that will just come into the picture here. Then in general, ln of z can be written like this, because you have seen you can actually rotate, no, because you see theta is there, right? So suppose this is again the argon diagram, and then let's say this is a complex number z, right? If I rotate this complex number by one full cycle, if I rotate this by one full cycle, that is by 2 pi, right? If I rotate this by an angle of 2 pi, what will I get? Again, I will get back the same my original complex number, no? So the number does not change. So z, which is equal to r e to the power I theta, this is z. If I rotate the angle, the same complex number, if I rotate this by twice pi, I'll again get back the same complex number. Okay, 2 pi radians rotation means it'll get back the same complex number. So I could just replace this, by I theta, I just replace with 2 to the theta plus twice m pi. Okay, so I can do that. Okay, small mistake here, it should be, this is not correct. Okay, it should be I, the bracket should be after this, theta plus twice m pi. Okay, this is what it is. So I'll make the correction in the slides. Yeah, here it is done correctly. Okay, so I into theta plus twice m into pi. So we can again write this down, ln r. So instead of I theta, it will become I theta plus twice m pi. So this is for any positive or negative integer m. So because you could rotate it either clockwise or you could rotate anti-clockwise. Multiplying, if m is positive means you're rotating clockwise. If m is negative, you're rotating, sorry, m is positive means you're rotating anti-clockwise. M is negative means you're rotating clockwise. That's the difference between the two. So powers and roots, the integer powers of z are unique. So if I raise z to the power of n, that's same as r to the power of n, e to the power I n theta. Powers are unique, but roots are not unique. Roots of z, they are multi-valued. Okay, so root of z, they can take multiple values. So that means nth root of z is n valued. Okay, and they differ by 2 pi by n. So this is what happens. Okay, so let's say I take, they differ by 2 pi by n. So what I mean by that is this. So let us say I draw the argon diagram again, the imaginary axis, the real axis, the real and the imaginary axis. So let us say I want to find out cube root of z. I want to find out cube root of z. Let's write it here. Let us say I want to find out the cube root of z. Cube root of z, when you evaluate this, you will not get one value. You will get three values, z1, z2, and z3. You will get three values. Okay, cube root of z, you will get three values. Okay, and these three values, they will be separated by 2 pi by n. So here in this case, when I say cube root of z, what is n? Root over nth root of z. So when I say cube root of z, n is equal to 3. So that's why we'll get three different roots. And what will be 2 pi by n? 2 pi by 3. 2 pi by 3 means what angle correspond to? 120 degrees, no? 120 degrees times 3 is 360 degrees, right? So this is what we'll be having. So if suppose this is z1, let's say this is z1, then where will be z2 and z3? Second, let me use a different color for this. So let's say I'm able to find one of the roots. Okay, one of the roots I'm able to find out. The first root, let's say I'm able to find out z1. The first root z1 I'm able to find out. Then what will be z2 and z3? Z2 and z3, very simple. Z2 and z3 will be separated from each other. Z1, z2 and z3, they'll be separated from each other by an angle of 120 degrees or 2 pi by 3. So this will be z2. This separation between these two, this will be 120 degrees. I'm writing it in degrees, okay, even though should be using radians. Okay, and this will be Z3 somewhere over here. This is Z3. This separation is also 120 degrees, and this separation is also 120 degrees. And if I were to draw an envelope around this, I'll find that the tips of all of these complex numbers, the tips, wherever this complex number lie, this is going to lie on the circumference of the circle. All of these, they are going to lie on the circumference of the circle. And what is the radius of the circle? What is the radius of the circle? The radius of the circle will be, if suppose Z is written as r e to the power I theta, okay, then r is the magnitude of the original complex number. So the radius will be simply r to the power 1 by 3. Okay, so all of them will have the same magnitude, that is r to the power 1 by 3. So consider a circle of radius r to the power 1 by 3, and all the complex numbers will remain there. Now tell me what will happen if I were to find out the fourth root of Z. Fourth root of Z, how many roots will I get? And what will be the separation between them? That is fourth root of Z. How many roots will I get? And what will be the separation between them? Can anyone tell me? Just use this. Fourth root of Z. Anyone?
90 degree separation.
Yes, and how many roots?
So 4.
4 roots. Very good. So we'll have 4 roots. So if let's say this is one root, okay, so we'll have 4 roots: Z1, Z2, Z3, and Z4. So let's say this is Z1. You immediately know what is Z2. Z2 will be 90 degrees apart because all of these, they are separated by pi by 2. So this will be Z2. Similarly, this will be Z3, and this will be Z4. All of them will be 90 degrees apart, and they will lie on the circumference of the circle. And what will be the radius of the circle? What will be the radius of the circle? The radius of the circle will be r to the power 1 by 4, where r is the magnitude of the original complex number. Fine? Is this clear? Okay, so we could write it like this: Z to the power 1 by n is equal to r to the power 1 by n e to the power I theta by m plus twice m pi by n for any positive or negative integer. Then importance, why do we need to learn? Okay, so far what we have done is we have just done a revision of complex numbers. Okay, only revision of complex numbers, but we are not interested in complex numbers, we are interested in complex variables. So we are talking about, so far we are talking about complex numbers. So we are not interested in complex numbers, we are interested in complex variables. And the moment we talk about complex variables, we can talk about, because variables, we are allowing the complex number to change, that's the meaning of a variable. We could start talking about complex functions, because after all, what is a function? Function is a mapping between one set of variables and another set of variables. Okay, so that's what we are ultimately interested in doing. So why do we, what is the importance, why do we need to study complex variables? Okay, so the importance of that is on the problem, the kind of problems that we can solve um, if we introduce the idea of complex variables. We can actually solve many physical problems using complex variables. Okay, for instance, the two-dimensional electric potential, okay, which is a solution of the Laplace equation. Next semester you have a course on electrodynamics, which I'll be taking. So over there, you'll learn about this Laplace equation and how to find out its solutions. What I'm talking about, you'll learn over there. Then there is a method called as conformal mapping. It is known as conformal mapping. It provides solutions to a wide variety of electrostatics problems. Okay, so this is one application. Another application is a time-dependent Schrodinger wave equation. You are familiar with the Schrodinger wave equation, which it contains an imaginary unit I, right? The Schrodinger wave equation is an imaginary. It's a complex function, right? Or is it a real function? The Schrodinger wave equation. The Schrodinger wave equation, is it real, or is it a real function or a complex function? Schrodinger wave equation. Are you familiar with Schrodinger wave equation or not?
So,
Right? The Schrodinger wave equation, most important equation for any physics student to know. In fact, you can you can print it out on your T-shirt also if you've seen that not don't seem to be able to remember it. Can anyone tell me what is the Schrodinger wave equation?
I cross
I h cross, yes.
side T
I h cross, yeah.
del side T
Dou psi by dou t is
equal
equal to.
to the Hamiltonian of psi.
Okay, but I'm not going to the Hamiltonian right now because that is you're talking about operators. So h
So,
cross square by
by cross f
twice m into
to
dou
psi
square psi by
del x
dou x square plus
d psi.
v psi. Good. So this is the Schrodinger wave equation, right? You can see this I, no? What is this I? This is that complex unit, that iota, right? So because this I has appeared here, when you solve this, the solutions also will be complex. What is the solution of a different? This is a differential equation, no? Solution of a differential equation are functions. So this will be the solution, psi of x comma t, right? So psi of x comma t, these are also, in general, they are complex functions. Yes or no? Because psi of x comma t, they are complex functions. Do they have any, the wave function psi, does it have any physical meaning? The wave function psi, does it have any physical meaning at all?
Psi
No, it
square.
doesn't. It does not have any physical meaning. Okay, it has got, it's the wave function psi has got relevance only within the confines of the Schrodinger wave equation. It does not have any physical meaning. What has physical meaning is this one has got physical meaning, or psi star psi. This has got physical meaning. What is this? This quantity. What is this? This is known as the probability density, right? It gives us the probability of finding a particle between x and x plus dx. That's the probability density. Yes or no? So psi by itself does not have any physical meaning. Psi star psi has got a physical meaning. So it means you are actually talking about psi star, means you're talking about conjugate. That means psi is a complex function. Okay, so the time dependent Schrodinger wave equation, it contains the imaginary unit I, and its solutions, in general, the solutions are complex. Okay, does anybody, just a question, just out of curiosity, I'm asking, does anybody remember where does this I come from in the Schrodinger wave equation? How does this I, creep into the Schrodinger wave equation? Does anybody know? Anybody? Do you know how this I, this one comes inside the Schrodinger wave equation? Anyone? I'll just tell you, okay, just out of, like, this is out of curiosity, okay, if you're interested. This is not related to what I'm going to teach. The Schrodinger wave equation, you cannot derive the Schrodinger wave equation. Can you derive it? You can't. Because the Schrodinger wave equation, it came from the mind of Schrodinger. Okay, there is no derivation for the Schrodinger wave equation, because the Schrodinger wave equation is a postulate. It's a postulate. It's the first postulate for quantum mechanics. Okay, so what we do is, we arrive at the Schrodinger equation using a simple system such as a free particle, okay, a free particle, and then we postulate that the Schrodinger equation, not only is it applicable for the free particle, it is applicable for anything. Okay, and in doing so, in arriving at that for the free particle, what we do is we use this relation: total energy is equal to kinetic energy plus potential energy. Yes or no? Total energy is equal to, this is kinetic energy. Do you agree? P is the momentum, no? Kinetic energy and potential energy. Yes or no? Now, what is E according to Einstein's hypothesis? What is E according to Einstein's hypothesis? E is equal to H cross omega, right? And what is P by de Broglie hypothesis? by de Broglie hypothesis?
H by
H
lambda.
by lambda, huh? H by lambda, right? So which I can write as H cross K. Yes or no? E is H cross omega and P is H cross K. Fine. So that means P square will be equal to H cross square K square, right? And this one, when you apply this on, when you apply this one, suppose I consider a sinusoidal function. When you consider sinusoidal function, if you take the first time derivative, if you take the first time derivative, what will it give us? It will give us omega into psi, no? And if you take the second space derivative, dou square by dou x square, what will it give us? It will give us k square into psi. Yes or no? So that means this k square that we got here, this k square, okay, this k square that we got here, it comes from, it can be replaced with dou square by dou x square, and omega that we got here, it can be replaced with dou by dou t. Okay, and whenever you are taking the first this one, whenever you're taking the first derivative of any of any sinusoidal function means if I take a function like this, a naught e to the power I kx minus omega t, if I take a sinusoidal function like this, if you differentiate it once, what will happen? This I will come, right? When you differentiate with respect to time, minus I omega is going to come in front, right? Dou psi by dou t is going to give us minus I omega, right? But when you differentiate twice, dou square psi by dou x square, minus ik will come again, minus ik will, sorry, ik will come again, ik will come, which will give us I square into k, I square, that is going to give us minus 1, so it will become a real. So the fact that you're doing single derivative, single time derivative, that is going to introduce this I here. Because you're doing single time derivative, it's going to introduce I here. Okay, so this I is coming into this Schrodinger wave equation from the single time derivative. Understood? And this single time derivative, where are we getting it from? We are getting it from E. And this E, where are we getting it from? This relation between E and P, where are we getting it from? We are getting from this energy relation. So the main reason why this I appears in the Schrodinger wave equation is this energy relation. Okay? If you're not able to follow this, don't worry about this. Okay, so I mean, this is not part of what I'm going to do. This is a little bit extra. That's what I'm giving you here. All right, coming back to this. So because the Schrodinger wave equation, the solutions are complex, so we need to learn about complex variables, complex functions in general. Then this power series solutions of second order differential equations. Okay, so if you have a second order differential equation, you can obtain a power series solution in the complex plane, and in that you replace x with z. Okay, then there is a process called as analytic continuation, and this analytic continuation, it gives us the solution. Okay, it gives us a general solution. So you just, from general, you come down to specifics, collect only the the real parts, that is going to give you the solution of the second order differential equation that we're trying to find out. Then this one, if suppose I consider, let's say, the Helmholtz equation in electrodynamics next semester, you'll come across this. Okay, sorry, this was in the diffusion equation. Okay, so in electrodynamics also we have a Helmholtz equation. So over there, when you make a small change, the parameter, there's a parameter in all these. Okay, the spherical and trigonometric functions, the Bessel functions, and all of these, there is a parameter called as k. That parameter, if you from k, if you change it to ik, then it transforms the Helmholtz equation to a diffusion equation. The spherical becomes the hyperbolic equation, and Bessel functions becomes the modified Bessel functions. So you really don't need to find out the modified Bessel functions from scratch. All you need to do is get the Bessel functions, make the transition of the parameter from k to ik, and that is going to give us the modified Bessel functions. Okay, so many different uses are there for complex variables. So this gives us a reason, because it spans a wide variety of physical problems. So it gives us a very good reason for us to study complex variables. Okay, so I think it's 1:49. What class do you have next? What class do you have next? Can you hear me?
We don't have any class.
Okay, fine.
No more
My class is still 1:45. Okay, so it's 1:49, and this is a good place to stop. in the next class. So this gives you a brief overview of complex numbers and the importance of complex variables. In the next class, we will look at some of these power series expansions. Okay, and I'll introduce to you how the functions of complex variables, how do they really work. Okay, so that's what we'll do in the next class. Any questions? Does anybody have any questions based on whatever we have done in today's class? Okay, so if you don't have any questions, then I think we'll stop here. I'll open that link for attendance, okay? I'll open that link for attendance, but unfortunately, that attendance link, it will accept only those who have student IDs, because one of the questions is you have to provide the last 4 digits, okay? I'll just show you here, okay? Just don't go to the link yet. Let me just show you here. I'll present my screen again. Just watch this, okay? Just let me know when my screen is visible. So when you click on that link, which I had sent, it will take you somewhere over here. Okay, you provide your email address, and then let's say you choose a name. Okay, so let me just choose Mehul. Okay, Mehul, what's your student ID? Mehul, can you hear me? Mehul, is he here or not? Yeah. I'm not able to hear you, Mehul. I can see that you're trying to speak. I can't hear you. Can you just text it, your student ID, in the chat? Can you just text this? Okay, so his student ID is DU 2020 MSc 0001, MSc 0001. So what you'll have to put is only the last 4 digits, that's all. Okay, only the last 4 digits. So my student ID is DU 2020 MSc. So if Mehul was doing this 0001, okay, and then you hit submit, which I'll not do. He himself will have to do this. Is that clear? So that's what you have to do. Those who have student IDs, only you will be able to give the attendance right now. Okay. So don't worry about it. Keep attending my classes. Okay. Later on, when you get your student ID, then automatically you will be able to enter this. Okay. So you all can leave. So those who have your student IDs, please give your attendance. Others, everybody, you can leave, and please join my next class. See you next week.
Thank you, sir.
Okay.
Thank you, sir.
Yeah.
Thank you, sir.